I'll be talking about measuring end-to-end security. So this is the result of a conversation. It came from a conversation I had with our CISO and one of my other coworkers, David. And so just a little bit about me. I'm the head of security engineering at Twilio. That includes product security, cloud security, corporate security, and we've just added automation engineering to that as well. So we're trying to automate a lot of our processes too. Before that, I was a startup architect at T-Cell. I've also done director of security for acquisitions at Salesforce. So a lot of work with smaller companies and bringing them up to a higher security standard. David could not join us today, but he is a principal security engineer at Twilio. Before that, he was an architect for both software and security. And he comes from a background where he was a good developer, whereas I was the bad developer. So you get both those sides and both those viewpoints in this presentation. And so the question we wanted to answer was like, how do we know our security program is working? What other measurements can we add? So in this talk, we're going to talk about the Twilio's SDL, our metrics that we started with, then bug postmortems. This is a process we added. I don't think it's especially new or interesting, but we're doing it in a very interesting way, I think. And then some new metrics that come out of that. And then we're going to talk about end-to-end security. So this is our process that's built around threat modeling. So we're not going to go through threat modeling. That's another class. But this is things that get added on to threat modeling that allow you to sort of measure your progress there. And then those metrics. And then if we have some time, we'll talk about where we're going next. So our current SDL or our previous SDL, has secure developer training. So people join the company, they go through secure code training, they go through security awareness training, and then as part of the process, we have threat modeling that we go through with the teams, depending on when what they're releasing and what features and how sensitive it is. We do 100 releases a week, sort of similar to the Slack team, and we just don't have time to block those. So we have a very rolling threat modeling process, and that is made possible with the security champions. So each team has a designated security champion on it that works with us either bi-weekly or tri-weekly, and we meet and discuss the features that are coming out, security concerns, and if they have any security debt. And so this feeds into the sprint planning and the secure development. And then we have a secure deployment process. So this will include things like making sure that when they deploy these microservices out, that they're secure by default, that we've done everything to make it as easy as possible to do the right thing and hard to do the wrong thing. From there, we have regression testing, which means like any bugs that got out into production before, we have tests in place for them. We do run that nightly. And then we have static dynamic testing, which I'm sure a lot of you are familiar with. We run several tools from third-party vendors against our code and against the site itself, including like OWASP, and just to make sure that we're covering as much as possible. And so for our continuous stuff, we have pen test and bug bounties. We have an open bug bounty. Anyone can sign up and take part in it through Bug Crowd to produce some good results. And then we also do annual pen test for the various products we run. And so the traditional metrics when we came in and we started discussing this was number of bugs found over time, say in a quarter or a year. We talked about the number of tools that we were running. And then we talked about what percentage of training coverage for engineers, annual pen test coverage, software that passed our security gate, or really it's a license to release to production since we don't block it, and the number of compliance standards that we've achieved. And so that's a good start, and we should be tracking these things. There's nothing wrong with those metrics. And you'll come up with all right, this is red, yellow, green. My security program's doing okay, right? I mean, but 3 tools, 3 compliance standards. I'm doing pretty good on annual pen test coverage. So what happens if I get to my goal, right? Like, what does that mean? I can go home. I can actually sleep at night tonight. That's going to be great. Like, am I bugs might still show up, but I'm doing everything I can, right? So you may think you're doing some things right, but maybe not. We want to prove it. So to illustrate this, we have two teams, one that has an SDL and one that doesn't. And we chart the number of bugs found over time. And so depending on how you look at this, you could say Team A is doing better because they're reducing the number of bugs that they're finding. You could also say Team B is doing better because the total number of criticals is actually smaller than the Team A's. And just to make it even tougher, what happens when this happens? You have one with an SDL and one without, and they both have the same number of bugs found. Like, is your SDL doing anything? How do you know? And so we want to talk about what evidence can we do to show that we're getting better. So the argument is we can measure bugs found. Great. I'm going to change the bug bounty to pay out $5 per bug, and we'll hire a cheap pen tester. I will have no bugs found, and I'll look great. And the reason is I don't want this situation where the bugs created 2 years ago, the features released, I add in my SDL improvements, start tracking metrics, and all of a sudden this bug's making my metrics look bad. And so the concept here is finding security vulnerabilities is not equal to a failure in our SDL. It's good. We want to get better at this. We want to find more. We want to add more. But we have to decide, what is a failure in our SDL? And so we started categorizing our metrics. So we have security coverage, we have security outputs, and security effectiveness. Our security coverage is how much of the organization are we covering. So this is percentage of developers that we're training. It could be percentage of products that we've addressed, that we're actually interacting with. Really it's, how much coverage do we have? And then we'll talk about outputs. So naturally, when we put these processes into place, there will be outputs from these things. Tools will find bugs, so we track the number of bugs. We'll talk about the number of developers reaching out to us from the security team. That shows sort of our engagement. And the number of issues or threat modeled issues, like how much threat modeling are we doing, what are their outputs. But none of these show that the security program's actually working. We can put all this into place, we can get up to our goal level, but we don't know if our training's effective, we don't know if our tools are effective. Something could still be failing here. And so we really need more data. So to illustrate this, we're going to take a stab at our first metric. And this is a conversation that came up as well as, why should a team self-report a security bug? We have 50 teams, they're working on features. Why should they self-report a security bug? It makes the product better. Yeah, it makes Twilio more secure. But their incentive is that their performance is based on how many features they ship, not how secure their product is. Maybe there's a reward. So I run into this a few times too, is we should give a small reward to the developers for every security vulnerability that they report or that they report from another team. Of course, being professional gamers of the system, we see immediate problems with this as far as, I'm going to stop talking up and speaking up in the threat modeling. I'm going to wait till my product's done, and then I'm going to start discussing these things. And so I came up with the concept of really developer security self-awareness. So this is, we bucket the reported issues into 3 ways. One is, they came up with in the architecture or threat modeling process, or it's been identified by the team during development before it reaches production, or it's identified after by third parties or pen testers. And so what we can see is, as the developer gets closer to this day 0, as these teams do, we know that they're getting more mature about their security, that they're finding these things faster. So we can compare that to bugs that actually reach out and are found by, instead by bug hunters. So to find this out, we're going to add in this bug postmortem process into our SDL. And so we're going to modify the bug postmortem process and modify a little bit of threat modeling. That'll be the end-to-end security part. And so this is really about getting the data we need to build better metrics. So the bug postmortem, it's traditionally been used just for incidents. I know some people have also used it for like serious security bugs, but I haven't run into an organization that does this, reliably. We do it, every 2 weeks. Somebody on the security team everyone's assigned a bug, and they present for 5 to 10 minutes on that security bug. And these bugs, at first, we narrow it down to things like customer reports, penetration tests, bug bounties, because just taking all the bugs from tools would be a little much. As we get better, we might expand into the pipeline as well. But we're going to start with highs and criticals, not every single bug either. And so what are we going to be measuring with this process? Well, the first thing is, when was the bug introduced? So we're either going to dive into GitHub, or we're going to talk to the developer teams, and we're going to figure out, when was this bug born? How much would we have paid a bug bounty researcher for this? So instead of using this is a P0, P1, we're going to assign a number. So we're going to go through our taxonomy and say, if this was reported by a third party, how much would we have paid? How much engineering time did this consume? So then fixing this, how long did that take? A couple of days? That's time that could have been spent developing features instead. And how much security time? My team does not work for free. The more bugs that we have like this, the bigger my team has to be, the more it costs the organization. So these are important things to track. The questions we want to ask are, really what area of security was affected? So that's authentication, authorization, was it output encoding? What feature caused this vulnerability? We match it up to a JIRA ticket. What part of the cycle was this found? Was it code check-in? Was it bug bounty? Was it a failure of the in-place SDL? So not just our all the SDL, it's the SDL that was in place when that bug was born, because we didn't add the entire thing at once. We pieced it in over time. So was this really a failure of some part of that SDL? And then was it a failure of training, design, development, or the pipeline? And if it's a failure of the pipeline, it was probably also a failure of one of the others. So it can be a combination of these things. And was it found live, stage, or check-in? We want to know. And of course, what would need to change? So this is our root cause analysis that we do. And as I mentioned, as the bullets we're going by, the estimated bounty is greater than priority. So we found that it makes a lot more sense for us to judge the importance to us based on our taxonomy and how much we would pay a theoretical researcher for this, as well as if it gets reported by bug bounty, we already have that number easily available. And so this is a small example. I threw in some sanitized data in there of some various bugs. Excuse me. And this is what a few weeks might look like. Is we find some failures of development and pipeline and design, and we notice that the bugs were born at various times. So it's not like these were immediately, they were all at the same time and we had all the same failures at the same time. So knowing when that bug is born is really key. So we have, so here's an example. I took the last set of data, and I'm going to bucket the number of bugs found, and I'm going to say in a feature. So for this, we're going to say features with critical vulnerabilities. So the numbers are number of features that have one or more vulnerabilities. And we'll keep it to criticals and highs as well. And then we'll have the number of developed features in that time span, and the bug bounty total that we paid out during that time span. So are we producing more bug-free features? Even if our bug count was going up during that time, we may find that during that time, we were shipping fewer and fewer bugs. We also might want to know, are we finding bugs faster? The lifetime of the bug is pretty important. So are we reducing the time it takes to find that bug from, say, a year down to immediately after it hits production? And so we can also track that using that bug postmortem information. Also important is, what parts of our SDL need to be improved. So you notice in the postmortem we asked what failed. And so we can map these numbers out to, what parts of these failed, what features shipped with failed things, and then we can sort of map that out with a trend line over time. Say, okay, failures of dev training, that's going down, that's good. Failures of development, that's going down. Failures of pipeline tools, uh-oh. So even if the total number of bugs went down, if you combine these graphs, the failures of design actually went up. And so we can see we have a problem there. And again, these are when the bugs were born, not when they were found. And so this brings us to our first security effectiveness metrics. The first one we talked about was the self-awareness. The next one would be the bounty cost per feature. We have a bug survival rate, so that's how long it's in production. And then we have our process failures. And so now we can take that bug postmortem process and feed it back into the SDL. So we modify secure developer training, we modify threat modeling, we modify like our interactions with security champions. We use checklist of what's going wrong, so we can modify like the top things we ask them about during our meetings. And then of course, anytime there's one of these bugs in production, we modify our regression testing as well. So one thing that comes up is, won't those stats continuously change? So the more I find bugs, that 4-month period may change. There may be additional bugs found because there'll be bugs born in that period that we didn't know about. Yes, and so for that we use a beta distribution. And this is actually based on our code written by our CISO, Richard Sarson. And so you can actually go online and check it out and modify it for yourself. But we continuously update this with the information to compare our beliefs, which maybe like 10% of the features will ship have a higher critical at some point in their lifetime, and say we're like 90% confident, 20% of the features or less will have a higher critical. And so we continuously add to this this data, and this just gives us better information. So beta distributions are based on hits and misses and statistics. So for hits, we use vulnerable features, and for misses, we use feature without a vulnerability. So next is the end-to-end security. So we wanted to find out not only like, are we getting better, but how well is our threat model actually working? And how effective has it been? So for this, we came up with sort of the idea of a perfect system, which is all features are threat modeled, every serious attack's been defined, all attacks are monitored, all serious attacks have controls, they all have, all these controls and monitors have continuous test. That's our nightly test that goes out and actually tests production for these things and validates they're working. And because of that, we can say with confidence that these controls and detections are effective. So to illustrate this, I came up with a really bad application, but we're going to sort of go through the process with this one. What's happening here is I'm going to write something on, say, Heroku. It has an app server, and it's going to call out to, you're going to log in with Google OAuth and give it permissions to get your calendar, so it can see who's invited to the meeting you're currently at. Then you're going to cross-reference that with the company directory, which is just a direct database access because you have really bad security. And you'll store that OAuth token and some profile information in a database for that application. There's also this microservice down at the bottom, which does some automated querying and says, like, here are the people you're going to be in the meeting with today. So where do we start? We start with really the PII inventory and usage. So this is all personally identifiable information. Our business case, our business assets and worst case scenarios for each of those assets, and our service connections. So the other microservices we talk to or that talk to us, and descriptions of what data is flowing between them. And we're going to feed that into our threat model. And threat models, unlike whiskey, can be blended, and you shouldn't feel bad. So use whatever works for your organization. It could be Stride, it could be attack trees. The important part is what's going to come out of this is a series of attacks that we'll work with. So the assets are going to be our PII, we're going to have names, emails, and our location, because we have that calendar information. Our business assets are going to be our company directory and the Google Auth keys, and so we come up with some worst case scenarios for those. And then we talk about the different services we talk to. Google Calendar and the microservice actually talks to us. And so since we have this information for a lot of our microservices, and we have a lot of microservices, we actually wrote a really nice tool, so I'm going to sidetrack just for a second and talk about something David wrote, which was Blackbird. And so this is an overview. We've sanitized the data a little bit here of our various products with each of their microservices. The globes are used for anything internet-facing, solid dot for internal service, and then we of course have database icons, things like that. And let's see if we can do a little demo movie. I didn't want to do a live demo. So what we can do is we can zoom out and move around all this information that we've collected about the PII, but we've also collected how these services connect to each other. So we'll drill into one of these services, and we can instantly get its different connections to various other services. And this is all a result of information we gathered with the teams during the threat modeling process. We can also pick one of the products and then just see all the services it talks to as well. So we can narrow it down by product as well. As you can see, we have several microservices. And so out of that, that process of threat modeling comes our attacks. And so we define several attacks. Of course, these are not going to be all of them, but we're going to start with an example of somebody could modify their last name to be Garrett held script, alert 1 script. And so when you log in and you see you have a meeting with Garrett, it shows that JavaScript. So we have a potential cross-site scripting. And then we're going to talk about our privileged one, which is we don't have any real logging controls, so an attacker could log into the application server, grab the OAuth tokens out of the database, and just grab everybody's calendar details. Then we're going to go back to our bounty idea and give each of these a bounty. So since we don't have any central way of stopping cross-site scripting, in the current design, we're going to say there could be up to 2 bounties there, like first name, last name. And then we could have, for the privileged one, that's not as big a deal. Let's say we gave bug researchers access to our internal network and they reported that. Sure, we'd document it and give them a $25 bounty for that. And now we're going to map controls to the attacks. So for each of these attacks, we're going to set up some controls as far as maybe we have the centralized templating library or strict CSP. And then we're going to have some detections. So that'll be our CSP reports. Then for each of those, we're also going to do that for each attack. And so there may be some overlap there between attacks and controls. So it's going to be a many relationship there. And so let's say that the strict CSP one, we say it reduces the bounty by $800 because that pretty much eliminates the cross-site scripting for if we get a really good content security policy in there. But the cost of the control to implement is around $10,000. Development time, research, security time, these are all just made up numbers, rough guesses. So we're going to do this for each of the controls and detections. So you may see that all these bounties are way less than the cost of controls. That is because the bounties are not equal to the expected loss of not having these things in place or of the attacks. It's really about just a way of having something that's very meaningful to us to compare to the cost of the control, and we build up that ratio. Based on that ratio, we can know what we're getting the best value for with our development time. And so we can make decisions here. So we're going to talk about, this is required before the product goes out. This, something might get backlogged, or it might be iceboxed. The cost of control is way out of line with like a $25 bounty. Or it may just already exist. So we can document that as well. The other nice thing the bounty theory gives us is sort of a way of determining trusted relationships. So we have this microservice X that can contact us, and through no fault of our own, it's got really terrible security, and it gets hacked, and somebody now has access to all that calendar information and PII. Even though our service was encrypting the tokens at rest, it had secure communications, it had authentication, authorization controls working, it really wasn't our fault. So we have this sum of trusted bounties, and so we look at that network that we had up before, and we can tell how much extra bounty debt, I guess you'd call it, are we adding to this app server? And so who should we really pay attention to here? Should we be talking to this team on microservice X and saying, you need to stop exposing your microservice to the public internet and pay, add some authorization controls probably, or something like that. But really, it's a way of development team saying you're dragging down my security to another development team. And the last part about this is validation testing. So here we just have one validation test per control, per detection, but you could have multiples. So for cross-site scripting, of course, or CSP, you'd want multiple tests running every night to test that it's actually working. And what that's going to give us is confidence in the fact that these controls and detections actually work. Not that we just placed them there, but that they are actually stopping attacks that we've scripted. And so you put it together and it sort of looks like this, where we have all this stuff feeding into the threat modeling process, and it comes out of it as these attacks that we can sort of monetize with bounties, and controls and detections that are mapped there. And so we have things like our flagship feature may have $100,000 potential bounty. It's residual bounties, $25,000 after we put in the controls, but the sum of trusted bounties, $45,000. So it's got a much bigger problem trusting these other services that are insecure. Whereas with the others, their bounties are much higher than the systems they trusted. But this tells us we may have controls that we haven't put in place yet, and so which of those controls that we put in place is going to give us the best amount of reduction for that residual bounty. And then, of course, we have that column of validation confidence. So how confident are we that that is actually true and that we've actually decreased the threat to this product? And so we add in two more security effectiveness metrics based on that, is the potential bounty mitigation and our validation confidence. And so these metrics together should be able to tell us, based on the coverage, based on our outputs, is our SDL effective? Is our threat modeling process effective? And how much are we improving? So you may have threat models in place, you may have controls in place. Just because you add another control, how much more secure did that make your company? And so without getting into, actually I'll talk about that in a little bit. But so what's next? It seems like a lot of this could be automated. So you saw Blackbird. It hasn't been fully automated yet, but we're working on it. We intend to open source a lot of this stuff, as well as the ability for developers to just go in there and enter in the PII that they're talking about. We work pretty closely with the legal team as far as when there's additional PII being used, we run it by them as well, so we serve a dual purpose there in case our privacy statement needs to be adjusted. So that could be automatically triggered. as well as those many relationships through attacks and controls. Obviously, that makes it for a great database structure. So, what else? We're quantifying the risk of our security work. So it's a little bit much for the granular like control and detection level. But if you put those together, you can talk about threats to the organization and actually quantifying those. So this is a book co-authored by our CISO. And from this, we can talk about like expected breach loss based on these threats. One thing I also like to talk about is expected loss of revenue from a lack of security features. And so we also work closely with our sales team to say like, okay, let's say we didn't have 2FA. How many enterprise customers are actually passing us by because of that? And so because of that security control isn't in place, there is a breach expectancy loss from that control not being in place, but there's also revenue that we're losing from enterprise customers, and it's probably larger than the breach expectancy loss. We can also do security bug survival analysis. So we had like our bug lifetimes and are they getting shorter, but based on the features that we're producing and how long those bugs are actually surviving, and we combine that with our beta analysis of like how many bugs are probably actually out there right now that we don't know about, we can map out how long those bugs are probably going to be surviving out there. And then we have our experiments. So how long were the developers with the company when they wrote the bug? This is a good one. We're also adding to the bug postmortem. So have they been on the team or with the company for like less than 6 months? And then they, by that time, they had figured out how to do things securely. So we could then like shift our focus to reviewing code by new members of the engineering organization. And so key takeaways here are, nothing is wrong with the existing metrics, but we want to categorize them. And we want to add to them to tell us, like, how am I doing? How am I doing at my job? And is it actually making a difference? I have security code training in place, but it was the wrong training. So, that's going to result in more bugs that are a failure of that training being in place. And we also want to understand, are we just getting better at bug hunting, or is there a failed process in place? And so that's the part about the postmortem and knowing, when was that bug actually born? And then it may be useful, to measure progress by, these easily understandable things like bounties, which are a lot more meaningful to both the security team and to others in the organization than the abstract concept of, a high, medium, low risk to the organization. All right, that's it. Thank you.